In this video, I want to do 3 examples of one-dimensional kinematics problems. This will help you with this week's assignment. So for all these one-dimensional kinematics problems, we have our 4 kinematic equations. And remember, they only apply when the acceleration is constant. So if throughout the trip, the acceleration changes at all, you would have to reapply all these equations. But most of our examples will have constant acceleration. Okay, you'll notice there are 4 equations. There are 5 variables. So the 5 variables are VI, VF, AT, and delta x. But each equation only has 4 of those variables in there, and which means they're each missing one. And so this VF is VI plus AT is missing delta x. The VF squared one is missing t. The delta x is VIT plus 1/2 AT squared is missing VF. And then the delta x, half VI plus VF times t is missing A. So this is how you're going to know which equation to use, because if the problem doesn't mention these missing variables, then clearly you don't want to use one that has a variable in it that you need. So this first question, you always want to start by writing out what you're given. So this is this Tour de France bicyclist who is passing over the crest of a mountain at an initial velocity of 15 meters per second, or sorry, kilometers per hour, and then goes down the hill, speeding up, and has a final velocity of 65 kilometers per hour. And his displacement along the hill is 4 kilometers. Okay, now you will always be told 3 quantities. You have to be told 3. You can't just make up 4 because they won't work in the equations necessarily. So, but you can just make up 3 numbers and then all those equations will work out. So the unknown, the 4th for this problem, is the acceleration. Okay, so that's what and so in this problem, you can see that we're missing t. It doesn't mention t, doesn't ask you for t. So we want to use the equation that's missing t, and that equation is the VF squared is VI squared plus 2a delta x. Okay, now before we use the equation, better check our units here. You could do it so that you get an acceleration in kilometers per hour squared, but most likely the computer is going to want meters per second squared. So we have to do some converting here. Now, the conversion factor that you should probably know, I have this one already written here, 1 meter per second is equivalent to 3.6 kilometers per hour. That ratio is 1. Now, whether you divide or multiply depends what unit you're trying to cancel. So if you've got 15 kilometers per hour and you want meters per second, you would multiply by that ratio. And so 15 divided by 3.6 is 4.17. 65 divided by 3.6 is 20.6. And then 4 kilometers is 4,000 meters. Okay, now it's a good idea to solve this equation for A before you put your numbers in. So A is VF squared minus VI squared over 2 delta x. And then you're ready to go. So you would have the 20.6 meters per second squared. It's always a good idea to put your units into these equations so that you can see that they all work out and you've got the right units. And then you would divide by 2 times 4,000 meters. A meter squared over a second squared divided by a meter is a meter per second squared. And it turns out this is not very big. 3.9 times 10 to the minus 2 meters per second squared. Okay, so that's the first question, and that's the standard approach to any of these uniformly accelerated motion questions. The next example is free fall. So it's someone throwing a ball from the ground. Now, of course, they're not going to throw it right from the ground. That would be the level of the hand, just as the ball leaves the hand. It's going to rise, stop, and come back down. And when it comes back to the level of the hand, we know the time. So the time of flight is 3.4 seconds. Now that's all you're told. And the question is, what's the initial velocity? So this is VI. So the unknown here equals VI. Now it also is actually a two-part question. It also says at what height did it reach? Let's focus on the VI first. Okay, now this doesn't appear like we've been given three numbers. You have to be given three numbers for one-dimensional kinematics problems. So how are we going to figure out what the numbers are that we're given? Well, first of all, is free fall. So you're always going to use negative 9.8. Negative, always, always, always. On the way up, at the top, on the way down, negative 9.8. Okay, now if we use the full flight up and down, we would also know that the displacement is 0 because it rises and comes back down. Now the problem and the equations, they would recognize that that's gone up and come back down to the same height. Okay, and then the time to do that is 3.4 seconds. That's one set of numbers you could use. Now, and VI, the unknown, is VI. Okay, so we could use the equation that has those four. That's the one missing VF. But that's not such a hot equation to use because it's got a t squared in it, and it tends to get students messed up. You could also use another set of givens. A is negative 9.8, always, always, always. But there's something else that we know here as well. We know that at the top of the flight here, VF is 0. If we just use the going up part as our trip. So if we're going to use that VF equals 0 at the top, we have to use the time just to go up to the top because these numbers all have to correspond to the same location in space. So the time to go up would be half of 3.4. Same time to go up. We're neglecting air resistance. So this would be 1.7. And then VI would be the unknown. So you can use, if you're going to use this set on the left, you would use that, oops, that delta Y is VIT plus 1/2 AT squared. But if you're going to do it the way on the left here, you could use that VF is VI plus AT up. Now, it sure looks to me like it's easier to get VI out of the equation on the right than it is on the left. So I'm going to do this. I'm going to go VI equals VF minus AT to go up. And so this would be 0 minus negative 9.8 times 1.7. And so this gives a VI of 17 meters per second. Now, we could do it over here as well, but we're going to have to solve for t here. And so that's not quite as well. It's okay. So this is 0 is VIT plus 1/2 AT squared. And so VIT is negative 1/2 AT squared. So VI is negative 1/2 A times T because you have to divide by T on both sides. And so this would be negative 1/2 of negative 9.8 times 3.4. And you can see you actually end up doing exactly the same calculation. Half of 3.4 is 1.7 times 9.8, and then two negatives cancel. And so you get the same number, 17. Okay, but that's an example of making a good choice of which equation is easier to use, given the information that you have. Okay, now if we want the height it reaches, so unknown number 2 is maximum height. Now, in general, I recommend don't use the number you just calculated, because what if you got it wrong? However, if you're doing this on Mastering Physics, at this point, it's going to tell you the correct answer. So what the heck, you may as well use it. Okay, so So what do we know here? So this trip up, we know VF is 0. Now, if we're going to do maximum height, we have to pick this point at the top, the maximum height where VF is 0. But now we know VI. And we know that that's 17 meters per second. And of course, we always know that acceleration is negative 9.8. There's our 3. The unknown here is maximum height. This would be delta Y. Okay, so which one should we use? We also know T to go up is half of 3.4. So now we've got lots of options for equations because we know everything but one. So we know T to go up is also half of 3.4, 1.7 seconds. So what's the easiest equation to use here? Actually, this one probably is easiest. Delta Y is 1/2 VI plus VF times T. So 1/2 of 17 plus 0 times 1.7. And that should give the maximum height here, 14 meters. Now we could use other equations too. We could use, remember they all work. We could use VF squared is VI squared plus 2A delta Y to get delta Y. And that would also, if put all those numbers in, you would get 14 for delta Y. Or we could use VIT plus 1/2 AT squared. So once you have 4 of the 5, you can use any equation you want to get the 5th one, as long as that equation has the variable you're interested in. Okay, so that's second example. Third example on this sheet is the one where you throw it from the edge of a cliff. It rises, falls, just narrowly missing the cliff to the ground below. So this is one of these ones that goes up and then it goes down like this. And so it's a stone and you're given the initial velocity. It makes life a lot easier when you're given the initial velocity. So VI is given as 15.5. You're also told the height of a cliff. Now be careful with this height. This is the height of a cliff. It has nothing to do with the stone. It's a positive number, but the displacement of the stone is what it goes in the equation. Okay, so we're trying to find everything pretty well. What's the velocity just before it hits the ground? How much later? What's the time to get to the ground? And then how high did it go? Okay, so let's get our givens here. Now, it depends what point we're going to analyze. How about we analyze, so this is point 1, and then this is point 2. So when we write all the equations, we have to make sure we're writing all the variables that correspond to point 2, given the initial position is point 1. So we're given acceleration is negative 9.8. Always, always, always. Now you do not have to analyze this separately up and then start all over again and down. The equations understand that if you're given an initial velocity of 15.5 meters per second and the acceleration is negative 9.8 the whole time, the equations know that this 15.5, the velocity is going to decrease by 9.8, decrease by 9.8, and keep decreasing by 9.8 until, I just better make sure it's still recording. Yeah, until it turns around, comes back down. So this is fine. You put the VI, 15.5. Okay, now what else do we know about point 2? So this is the entire time. Point 2, we know the displacement of the stone is negative 75. It has gone down, and so that's why the displacement is a negative number. You have to put that negative number in. Okay, well, there's our 3. We only need 3. So what do we want to know here? We want the velocity and we want the time. So we want the other 2. So let's just do velocity first. So what's VF? Unknown. Once we have that, then we can work out the time. It's always a good idea to find VF before you find time, because remember, the equation that has time squared in it is a quadratic and it's nasty. So we try to avoid that one. Okay, so this is the one missing T. VF squared is VI squared plus 2A delta Y. Now, remember when you take the square root, you have to go plus or minus the square root of vi squared plus 2a delta y. And you have to pick. Well, we're going to pick the negative because we know the thing is traveling down just before it hits the ground. Okay, so you have to pick negative because velocity is downward. All downward quantities are negative. All vectors that point down are negative, whether it's acceleration, velocity, displacement, doesn't matter. If they point down, they're negative. Okay, so this is negative square root of initial velocity 15.5 squared plus 2 times negative 9.8 times negative 75. If you didn't put the negative displacement here, you'd get an error. Okay, so it turns out that the velocity, it's a big velocity, is negative 41.4 meters per second just before hitting the ground. Now the time down there, we can use whichever equation we want now, the easiest one. So now unknown number 2 is time. So let's see, we've got everything but time. What's the easiest one? I think this is probably the easiest one. VF is VI plus AT. And so T would be VF minus VI over A. Now be careful of the negatives. VF is negative 41.4 minus VI, which is 15.5 over negative. And of course, the time has to be positive. So if you didn't put that negative 41.4, it wouldn't have worked out. Okay, and this turns out to be the time to get down there is 5.8 seconds. You should definitely confirm that that's correct. I'm just reading off of a solution here from the textbook. Okay, and then we want to know what maximum height it reaches. So unknown number 3 equals delta y at max position. Okay, so we have to start again because now we're looking at a different point. Now this is point 3, and so all our numbers have to go together. VI is always the same. How high the cliff is makes no difference here. So we still have the VI, 15.5, that's the same. And we still have the acceleration. So our givens are a little different. That one's the same. Acceleration is the same. But now we're talking about point 3. We need a new given. Well, delta y we don't know, but we do know that the final velocity up there is 0. That's our little clue here at top. Okay, and delta y is the unknown. So once again, we have an equation. There's no time in it. And so we're going to use this one, the VF squared is VI squared plus 2a delta y. So delta y would be 0 minus 15.5 all squared. The minus stays out front there, divided by 2 times negative 9.8. And so we have a positive number for going up. And this turns out to be 99.5. Wow, it really goes up high. Oh, that's wrong. It's 12.26. Yeah, that seems crazy. That's 12.26 meters. Okay, so those are the questions that are going to help with your next assignment.